So I'm not able to see the rest of the audience, so I'm not able to see the chat as well. So if you have questions, I welcome them. Just please talk, because that's the only thing I can hear. At this point I can only see my own slide presentation. So thank you very much for that introduction. I'm going to talk today about a subject that is pretty close to my heart, because I've spent the better part of the past couple of decades thinking about it. Tackling long-standing verification challenges with ML. My affiliation is with the University of Illinois at Urbana-Champaign, where I am a professor, but also with Google Research, the Brain team in particular, where I have been visiting for the past couple of years, and I'm continuing that arrangement. So some of the research that I'm going to talk about is from our research group at UIUC, and some of it from what we from recent research at Google Brain. So I'll start by saying that systems of today and the systems that we are going to build tomorrow are complicated, very, very complicated. Uh, we are coming up with all kinds of efficiencies or particular hardware that is designed for machine learning, or designed for the kinds of systems that we are that we have started using. We have departed from Van Gogh. Departed from the von Neumann model of architecture for a very long time, and now we are into specialized architectures, and to the point where our demands from consumer hardware or has become almost unreasonably high. So we want mobile hardware with sleek form factor, which is light, which is low power, which is a high battery life. We want desktops and servers that have followed, the desktops and servers that have followed Moore's law are basically 350 times faster than they were in 1990. The systems that we want right now are highly parallel. They are sometimes hyperparameter parallel. There are new architectures for almost every single learning application, and all of them are highly data intensive. So with all of these huge changes in hardware and architecture, uh, there's no free lunch. We know that, right? So if there is no free lunch, then who's footing the bill for all of this? And I am going to argue that the people who are footing the bill are the ones who with the job of verifying this hardware. So verification has always been very hard to begin with, because it is a very hard problem to scale because of the scale and the complexity of that problem. We have always built systems that we do not know how to check. And it's almost like verification is an afterthought. So design is the thing that we do first. We architect the systems, we dream up things that we want, and then we think about how to check them. So the onus of getting it right is always on the folks who have to deliver that verification, that system is correct or is verified. So what is verification? Verification is proving or is proving that that an implementation is able to satisfy a specification at the most fundamental level. In the case of hardware, that implementation is usually at the logic level, and the specification is in the form of some kind of a high-level English document or a C++ model or something. There are different artifacts which are used in what is called design verification, pertaining to RTL implementation verification. And these kinds of artifacts include tests, assertions, cover points, simulation, emulation, etc. Different ways of trying to ensure that the implementation does exactly what does what is intended. So why is that problem hard? And why do I think that the price of the lunch is being paid by the complexity of verification? A 300 flip-flop design has more state than the number of protons in the universe. There's about 10 to the 80 protons in the universe, and an ALU generally, or a design with a small wishbone protocol, has much more state than that number. We build systems with many billions of flops. So the kind of complexity that we are talking about, in order to correctly answer the question, does the design satisfy the specification? That complexity is impossible to achieve with the systems that we have built. Okay, so it's plain and simple. It's basically impossible to navigate 2 to the power of billions of states and be able to conclusively state that our implementation always satisfies the specification. This is why verification is hard. It has been declared a grand challenge of computer science for more than 3 decades now. And given that it is basically impossible to completely analyze the kinds of complex systems that we build, the next best thing in verification is to basically make it a best effort. So we still tape out chips, but we are taping out chips as a best effort, with the best effort we can in verification, because it is accepted and known that we would never be able to check anything that is remotely close to the kinds of systems that we build. So given that, what are the challenges in hardware verification? The first challenge is, how do I scale a tool to check many billions of states? The second the second challenge is, given that I cannot scale a tool to check many billions of states, how good are the tests that I'm writing to check some part of the state? Am I testing what matters? So given that all of this now becomes about best effort, the next question is, how much am I covering? How do I know when I'm done? And then there is the question of, how do I know what to look for? So when it comes to tests, I know that I have a desired input that should look like a desired output. I know how to compare my implementation input-output with my specification input-output. That's at least tractable as a problem. But how do I know about things that are not in input-output format? Like if I want to check if some of my devices are being starved of resources, or if my priority arbitration protocol is unfair to some devices, things I cannot check with input-output as easily. I would then have to generate good properties or assertions for them. How do I know what to check for? How do I know what to look for? Then there is the classic question of, am I checking all the bugs? Am I finding all the bugs? Are my tests good enough to at least debug the system? And once I have a bug, how do I diagnose across millions of simulations? Can I replay the bug? And so on and so forth. So there's multiple very, very challenging questions in hardware verification. And these questions are intellectually complex because of the kinds of state space that we just talked about. They're also practically, it turns out that in the practical sense, these questions can be showstoppers. So what does that mean? Verification tends to be the main bottleneck, whether it is hardware, whether it is software, or embedded systems, or SoC systems, any systems. I have spoken with people across multiple different industries, including starting from NASA to small ASIC companies. If they are if they are building any kind of system with or without hardware, verification, the testing part of it, where they check that everything that was desired is in that system, that part of it is the main bottleneck. So it's known as, so often called like the 70-30 or the 80-20 rule, where 70 or 80% of the resources are spent in the verification of the thing, and 20 to 30% of the resources are spent in the design or the development of the thing. And that thing, and these numbers hold true whether it's Microsoft or whether it's Intel or whether it's software or hardware. Typically, the kinds of the tests, the number of tests, or this can vary from company to company, and these are not specific to any particular company, but the across the board of all across a decade of these conversations, this is typically it takes between 3 to 6 months or 3 to 5 months to generate all the tests that are meant to design, that are meant to verify the system, part of the verification suite. And it then takes around 10 months or 8 to 10 months, depending upon the number of people on the project, to debug and diagnose failures and to actually generate coverage closure. And coverage closure means 100% coverage according to the coverage metrics that have been widely accepted as good enough. Again, there is a philosophical question about whether these coverage metrics are good enough, but we will not even get into that, because even without that, just ensuring that all the coverage metrics are hit and that there are zero bugs, this process can take a ridiculous amount of manual effort. It takes about 15 to 20 verification engineers a year of manual effort, or at least 8 months of manual effort in a typical industrial setting. And that is a lot of productivity. That is a lot of engineer time. That is a lot of compute resources. And all of that is being poured into this problem because we don't have a good way to solve it other than just throw more and more simulations at it. So this is again not an example of any one company, but a very typical example of what might happen when you're trying to put together a typical, even moderately sized system together. Let's say you're putting together an AXI master and an AXI slave. There would be at the unit testing level, the AXI master and the AXI slave check out really well. They follow all your tests and they're able to generate the exact output that you expected in simulation. But when you put it together, this doesn't happen, and you don't even detect that during your RTL development and simulation phase, but you detect it during the post-silicon phase, because the bug was a corner case data read or write request that caused a severe deadlock. And that was a particular deadlock that you did not think about while writing your properties or while writing the tests, and you never came across it, but you found it in the lab after hours of post-silicon validation. And then if you're a company that does software, you might do a software workaround, but if you're not, then you're in trouble. So this is the kind of very typical scenario which plagues modern industrial verification. So pertaining to this community, where does ML come into this mess? So to answer that, let's take a slight step back on the on the use of ML for this problem. So some of this, so we will be revisiting this pyramid later in the talk, but for now, I think to get an understanding of how why ML for this problem, and how ML can contribute and has contributed and will contribute for this problem, I think is a good way to structure this discussion. So we will start by looking at two different kinds of solutions on the spectrum. One kind of solution is dynamic analysis or simulation. The other kind of solution is static analysis, which is exact representation, that is that's based on exhaustive methods. So if you look at these two types of verification techniques, the static analysis approaches are basically what you would traditionally call as formal verification. So while formal verification holds for gate level analysis, typically is done at the state transition graph level for gates. A static analysis is a more is a more PL kind of terminology, programming language kind of terminology, which refers to analyzing the model of a system. So that model can be a program, it can be RTL source code, it can be a higher level abstraction graph than, say, a state transition graph, but whatever. The point is that the takeaway or the way to understand static analysis is analyzing an exact model of that system. Okay, so analyzing or a very faithful representation of that system. So static analysis is able to do exhaustive analysis. Since it has a complete representation of the system, it can completely analyze every state of the system. The problem with static analysis is that, as we talked about, it is impossible to scale this kind of an algorithm to anything that would be feasible or relevant. And in some sense, it needs infinite space, which is in memory. You can think of it as if we had infinite memory, then static analysis is an ideal solution and we could go for it. But unfortunately, we don't have infinite memory. On the other end of the spectrum is dynamic analysis or simulation. As it turns out, all of industry has gravitated towards that part of the solution. So the example that I was showing you with AXI protocol and telling you why this verification is practically a nightmare, that practical nightmare is because the reliance is completely on dynamic analysis or simulation. And what dynamic analysis means is that every single execution of that design is represented as a concrete single representation, is a single simulation. And this is, of course, scalable because you can simulate the total, you can test you can write as many tests as you want, and you can run as many simulations as you want, and you can declare victory when you want. So it's kind of so it's scalable in that sense because you're only analyzing one concrete execution at a time. And of course, it's practical. That's why it's used in industry. But what's interesting here is that it takes this problem of infiniteness in space and translates it to infiniteness in time. What that means is if you could run, quote unquote, infinite simulations, like if you could run these simulations forever, then you would be able to completely verify your system, but you cannot run forever. So there, the constraints are more practical. Like, oh, it's already 6 months, and we're in the red zone for verification. So let's quickly call it quits and say that we are frozen the RTL and things like that. So there's the problem of infinite space is now going to be the problem of infinite time. The complexity hasn't gone anywhere. It's just presenting itself in a different way. That's all. And the problems in simulation are that it's ad hoc, unsystematic, and it is a manual time and resource sink. So in the context of ML, I see ML as contributing to verification by doing some kind by providing some kind of a via media between these two types of algorithmic or these two types of approaches. So there is, of course, for the sake of completeness, I must talk about the combination of static and dynamic analysis. And so these are with hybrid representations between the two, and having dynamic analysis guide with static analysis, etc. And these kinds of techniques also tend to have limited scalability, although they are much better than plain static analysis. They tend to be fairly impractical for anything that is relevant in modern industry. And the time and space requirements tend to go out of hand very soon, even there. So then we come to the final part of this puzzle, which is the concept of applying ML, but with under the guidance of the static analysis. Okay, so what that means is, so this is so number three is where I have spent a lot of my research time thinking about that space of solutions for verification. So given that ML, so the attraction for me to do this kind of analysis is that ML by itself uh, has the advantage of statistical analysis. And statistical analysis by nature is dynamic. It relies on data. It relies on the kinds of things that the simulation, or the kinds of information that the simulation already generates in a typical verification environment. So initially, when in some sense, that information can be culled, or that data can be culled or mined for analyzing things that are not obvious, or that need machine inference, because it's not obvious to the human eye. On the other hand, these designs have been, they have excellent CAD algorithms in terms of like formal verification, or in terms of static analysis approaches. There's excellent ways, whether it's cone of influence, or whether it's program slicing, or whether it's BDDs. There's a lot of different analysis approaches that rely on exact static representations, that have a very deep knowledge about that system. So in all of my research, my approach has been to be able to use these two together in tandem, to be able to use static analysis that exists in CAD for verification, and to be able to use it effectively with different statistical methods or ML-based methods in order to exploit, maximally the use of ML. And so in some sense, what I'm going to show you for the next few slides is going to be examples of that kind of static analysis plus ML approach. Towards the second half of the talk, or the second, or the I should say the one third of the talk, I will be talking about an approach that is different from any of the stuff that we see on the screen. And this is this is kind of a recent big insight that we have had in this entire space of ML for design verification. And that's probably that's probably the most the part of the talk that you've never seen before. But for the next part of the talk, I am going to give you examples of doing this kind of taking a problem and applying ML to it with guidance, with very close and sort of smart guidance from static analysis. And that smart guidance is algorithmic. It's using whatever existed in literature as static analysis, but it's just providing it in interesting ways to ML. And although these are very scalable approaches, these approaches, category 3, still has a small snag. That category of solutions has a snag. It's much more scalable, and it's much less time and resource intensive, but there is a cost to it. And that cost is what I'm going to talk about, and hopefully argue for how we can alleviate that cost with a different kind of approach. And the cost is in being able to do this kind of feature engineering or handcrafting for each problem, where you figure out how to combine static analysis with ML to make it work for that problem. So there is a good number of problems for which we have generated and applied solutions from my research group in UIUC. And I will be very briefly touching upon a couple of these, because I want to quickly get to the new insights and results. But to just give you a context of, since we have been working on this problem for more than a decade now, I think there's something to be gained from our experience applying ML to different verification problems, including coming up with good coverage, generating good coverage metrics, generating good properties or invariants, coming up with high quality inputs, test inputs for simulation, converging on coverage closure faster, or being able to do post-silicon validation and debug. And even taking this problem to analog verification and to system level verification, which is high, transaction level, or where the validation is mostly not functional but performance. We have tools and methods for all of these, and almost all of them follow that philosophy of being able to grab an existing good solution in static analysis that would never scale, and then infusing ML energy into it in the right point so that it now becomes a spanking new algorithm that can do so much better. So I think most of these insights I have touched upon, and we will talk about them later as well. But I think the high order bits from this part of the research, from applying ML and static analysis on a problem by problem basis, from that part of the research, it turns out that almost in every case, guiding the ML algorithm with model or design information helps the ML algorithm focus and converge extremely fast, and to the orders of magnitude fast. And I'll show you some results, hopefully, to hit home that point. There's also the mode of providing this domain knowledge is different for different verification problems, like the different ones that I showed you on the previous slide. Those are all different tools, multiple PhDs per tool. So it has each of them has a different flavor of providing the static analysis knowledge. Engineering domain relevant features instead of raw features is very valuable. And again, the more sophisticated the domain relevant features, and our focus has always been on automatic methods to do all of these things. So automatically extracting domain relevant features always helps greatly over the raw features. And we find that in almost in every case, the ML algorithms are good at inferring the structure of the design and solving ancillary problems that we had not anticipated going into this question. So I'm going to, so the ways in which we have made ML interact with verification are we use ML as a guessing agent from simulation data, and then we use some kind of a oracle to validate against ground truth. Sometimes we have done this kind of iterative feedback from the model to the ML algorithm, to the guessing agent, and then done model guided inferencing. And so in each case, we've actually gone a different route to make these two work in tandem. So I will give you 3 examples. I'll give you an example of assertion generation. I'll give you an example of test generation, and I'll give you an example of silicon debug. And for all of these, I cannot go into great technical detail, but I will tell you the general high-level idea and what we saw when we applied that idea. So in the case of the first problem, which is invariant generation, we basically applied the idea of using ML from simulations as data, and being able to, and then we used static methods like cone of influence and BDD based methods and control data flow graph information to inform the machine learning the machine learning that came out of data simulations. So the context, of course, is that Goldmine the first paper appeared in 2009, much before machine learning was the kind of rage or as big a deal as it was today. So it was early days for applying ML and CAD, and so the earliest papers in Goldmine are much more the algorithms are not hardly as sophisticated as what you would see in MLCAD today, but it dates back to like 2009. So we started there by basically saying that the ML was scalable, but when it lacks context, it generates garbage. And on the other hand, static analysis is not scalable, but it has the complete context of the design. So we combine both, and Goldmine has done pretty well and is able to and has is currently being used in a lot of different EDA. EDA products. It has been developed into a commercial product as well. It's also available for research use. So please feel free to contact us and use it for your Verilog design, generate assertions, generate invariants. If you're doing a course teaching RTL or teaching students how to build hardware designs, then this is a good way to actually provide a check for whether the designs are correct or not, because the assertions can actually the assertions they generate on their design are often used as grading artifacts by different TAs for checking their student designs. So Goldmine had its successes, but the point but that's relevant to this topic is that there are multiple simple algorithms that we used in the beginning to kind of give the flavor of generating assertions from simulation data. And these are very vanilla non-deep learning ML algorithms. And in many of these cases, we actually generated our own algorithms as well, like the coverage guided association. And the static analysis part of it, there was much more innovation in terms of how to provide that static analysis. So in many cases, we did counterexample based guidance. So we would run this Goldmine engine through a formal verification tool, and then whatever counterexamples were provided by the formal verification tool, we would use that to guide the machine learning. At some point, we also did a bounded cone of influence that we provided to the machine learning tool. In different cases, we also provided for an assertion how much coverage that assertion had, and we developed static analysis methods to come up with methods to find coverage of an assertion in RTL. And then that's the information we provided, and the machine learning algorithm took that information and then generated invariants which were of higher coverage. And we also took symbolic simulation at the word level, which is not our invention, but has been invented for other purposes, and tried to provide that as those words, word level information as targets and features for the machine learning algorithm. We then went on to do evaluation of the assertions that we had generated, the invariants that we had generated, based on a number of different criteria. And these criteria were again provided. We developed static analysis methods to analyze these, to evaluate the assertion based on these criteria, and then we provided that to the machine learning algorithm, and the ML algorithm just kept refining its learning based on this kind of evaluation. And this turned out to be extremely valuable, because here is an example from for a Goldmine assertion for a PCI bus master, which is a very typical design, and the kinds of assertions that this tool was able to generate, mainly because of the machine learning, is because of its ability to scan through the entire RTL and be able to come up with very complicated relationships which are temporal across different cycles. And so if you see this A1 assertion over here, this tells you that it's across multiple cycles, but it's also spatially in different parts of the RTL. So it can scan across different parts of the RTL, and it's able to, as it turns out, it's ranked the highest by the internal evaluation system, because it captures probably the most important functionality in that design, in the PCI design. So that's basically that provides you probably a flavor of the kind of technologies that we try to investigate in order to come up with the outcome of generating the best possible assertion. Of course, this is that the assertion can be thought of as a summary of the entire design more than as a foolproof assertion, because it's being generated from the RTL itself. So Goldmine had its limitations in terms of in terms of value beyond RTL verification, but in this case, this was the use case. Now, moving on, learning. So in the case of input stimulation, how did we use input stimulus generation? How did we use ML? Well, as I told you, there is a, so if you think of the assertions or the inferences, rules that are generated from the simulation traces as passing through, we passed it through a formal verification engine, and whatever was a real rule passed as an, and we called it an assertion, but what was not a real rule, and it is true only of the simulation data that had been seen by the, in this case, the decision tree, that was considered a counterexample, and that counterexample was simulated and added to the simulation traces, and the decision tree was rerun on this kind of simulation trace. And what happened in that process is that for every such counterexample that the formal engine generated, we started to append that and generate incremental decision trees. And here is where we observed that it's really fast to converge, starting from completely random data with just a few counterexamples from formal, of little bit of feedback, like few iterations. It was possible to basically converge to the entire functionality of a given output. So in this case, like output Z, within 2 or 3 iterations, we would see, even for outputs in moderate size designs, we would see that the convergence was really quick, and the final decision tree over the learning, the final decision tree was actually functionally equivalent to a BDD, and we proved that in the paper. But the point here is that it's possible to converge very quickly to the complete functionality of that output just through iterative this kind of iterative feedback from the formal engine, right? Because it's sort of like without that, when we try to apply this in the same test generation without that feedback, the amount of time that it would take for the learner to actually come up with a set of tests that are that can capture even some portion of the functionality would be would take multiple iterations to get there. So this is great in terms of an insight as to how much even a small amount of a focused guidance can help converge very quickly. In the case, can help a learner converge very quickly. However, in practical terms, we were limited here by the size of design that the formal verification could handle, because that's what we were using to focus the machine learning engine. So of course, we then moved on to other kinds of static analysis, not just complete formal verification, not exhaustive verification, but different other kinds of analysis. And we were successful with I would say to varying degrees. Sometimes we were really successful in some collaborations. We found that we were able to generate a very high coverage and tests with this kind of a ML-based approach. But in cases, it was not able to come up with the best set of tests or learn the functionality, because in the absence of formal analysis, it was not able to converge as quickly and focus its learning. So another case study of where we applied machine learning, so I've showed you two. One is assertion invariant generation, and the other one was test input stimulus generation. And this one is post-silicon debug. And so we started out trying to frame post-silicon debug as an outlier detection problem, where normal behavior would be correct behavior or expected behavior, and buggy behavior would be outlier behavior. And then we could use outlier detection algorithms of which there is plenty in the machine learning literature, and repurpose it for our own purpose. But as it turned out, as I said early on, and kind of has been the theme of my research in all these years, is that it's impossible to apply a machine learning algorithm as is to any of the design verification problems. So although there is plenty of outlier detection algorithms that do exist and they're really sophisticated, in order to make it work for this domain and for this specific context, we found that there was the way in which the domain information had to be provided to these outlier detection algorithm was incredibly important. And now it's not, in the previous case, I showed you examples of how we did static analysis of the design and provided it to the ML algorithms so that it could come up with better assertions or better tests and so on. In one case, we used formal verification. In this case, none of that is possible because it's because of the nature of the problem, because of the fact that we're running millions and millions of tests, and some of these tests failed, and at the end of that, this is a completely black box system where we don't have the luxury of this internal analysis that we were able to do in the pre-silicon case. So in the post-silicon case, we only knew that there was a bug, and then we had to kind of work in this very black box environment that is inherent to post-silicon. And what we found was that the only way to do an effective analysis was to do some very sophisticated feature engineering. When I say sophisticated, it's all automatic algorithms. The focus is on automatic algorithms. Of course, manual feature engineering is possible, but that was not. But our interest was to be able to generalize this to any hardware design. So, given a hardware design, how would you be able to apply to debug that design, given with just the post-silicon traces? And what we found was that, so if you look at this example post-silicon trace data, then for the raw features, the raw features provide message-specific information, and the outliers are not well demarcated. So in some sense, we had to, so that's what I mean by having to generate our own features. And these features, the features that we generated, they had much more context for detection than the raw features themselves. So the kinds of, so after coming to the conclusion that we cannot use raw features as is for outlier detection, we basically engineered very sophisticated features to control the normal, to kind of demonstrate the difference between the normal and the buggy behavior so that the ML algorithm could recognize the bugs as the outliers. So what was this feature engineering? Well, you can of course read the papers for more information. But the kind of feature engineering that we use, the kinds of features that we decide to incorporate, those are things like infrequency of buggy message sequences, and and the extent of deviation from bug-free message sequences. So we took these types of features, and then we tried to find them automatically, the ones that were infrequent and the ones that were very deviant from the bug-free message sequences. We would flag these, and then we would be able to call those as automatically generate the features around those kinds that had those characteristics. So anyway, so at the end of this, of course, we did find that we were able to do that the outlier detection algorithms were able to do an excellent job of categorizing something as buggy or not, given this feature engineering. And then we went on to apply this to different systems in multiple collaborations that we had for this work in post-silicon. But moving on to this pyramid figure that I promised we would revisit. So we have definitely talked about all these four aspects, these four different solution spaces of targeting, of solving the design verification problem. And I had told you that number 3 was my preference, or was I'm attached to number three because of all of these solutions and many, many more that I've not presented here that ended up working for us and working excellently in many of the cases. But what was the problem with them? As you saw in each case, even to a shallow extent that I was able to describe, we found that in each case, whether it is feature engineering or whether it is coming up with static analysis algorithms, in each case, there was a decent amount of handcrafting that went into figuring out how to use domain information for ML, to make ML useful. So in none of those solutions is there a manual component. But the manual component, or the ingenuity in figuring out exactly how you can make this existing domain knowledge useful so that ML can be used automatically in a push button way, that ingenuity had to be, as I said, multiple PhD theses per problem. Is there a way, is there a workaround this which would make it much more generalizable across the board for design verification problems? And that's the flavor of the kind of work that we have been looking at while at Google. Is it possible to use deep learning for some of these problems? And in our experience, we know that ML has been, deep learning has been used for software systems, for scaling analysis beyond static analysis, and multiple compiler optimizations, testing, debugging. For software systems, this is a very thriving area of research. And the question is it possible to do this kind of a deep learning approach for a hardware design, for solving all these problems which are so daunting in intellectual as well as practical terms? And so, in other words, the question that we are asking is that, given an RTL, is it possible to approximate the design state space in a way that can serve, that can make, so in a way that deep learning can serve as a design proxy? So if you think about it, deep learning is really good at coming up with proxies from data for how to for problems like how do you recognize a cat. It comes up with inferences or summarized methods or some approximations, function approximations that can figure out how to summarize the data in the best manner possible. And this is its power. And it can do it for problems like recognizing cats, or being able to complete sentences, or being able to translate sentences, and so on, or even search. But in all of these cases, it uses traditional data sources like natural language or images or even videos to be able to infer and recognize or understand. In a sense, what it is doing is it is approximating or summarizing all of the data that it sees into very sophisticated functions. So the question here now becomes, is it possible to look at RTL data and to look at RTL representations, whether they are in natural language or whether they are state transition graphs, so whatever is the way that we understand RTL, is it possible to make a deep learning engine understand this RTL and summarize it and approximate it so that it can now serve as the design proxy? It can know everything about the design. And why do you think that would help us? Well, as opposed to the case of computer vision or the case of NLP, we are not looking to do the same thing as a human being can do in this problem, right? We're not trying to say, I can recognize a cat. Can the AI ML engine recognize a cat? That's what a human being can do. Or, okay, I know how to complete a sentence. Can it complete a sentence? We're also not looking to see whether a certain movie that I like is recognized as a movie that if a certain movie that I would like can be recommended to me like a human being would recommend it to me, or can it be culled from the space of all movies that a human being cannot do? So the kind of problems that we have used deep learning for have been in that space. What we are asking here is, if we do this kind of approximation and summarization of the design state space, can it help us scale? So this is a very novel way to think about the deep learning problem. The only close, I'm sorry, to think about the deep learning solution as a way to help us with our current problem. And the only, as I said, the only analog to this kind of thing is in the programming languages world, where deep learning has been used to understand some aspects of the program. What we are looking to do here is much more. In some sense, we are trying to learn the design in a way that all of these problems, test generation, coverage closure, assertion generation, and everything else should come for free, because this learner has learned everything that is relevant about that design state space. So this is the grand vision that we are thinking about. And I don't have time to go through a lot of the different reasoning as to why that behind the vision, but I will mention that typically abstractions have in hardware verification or in software verification have focused on being very property specific, like condition, like CGAR, or based on program slicing and so on. Or they have been based on language, language specific, like specific to Verilog or specific to something else. They would be generating abstractions that are cognizant of that language. But in our case, the kinds of things that we are talking about would be the abstraction or the summarization of that design state space is using a neural network. And that's the vision. So it's not, so abstractions have been used in verification before, of course, but they have been used in a very handcrafted, or in a very in an algorithmic manner. Learning has not been used for it. And the idea is that if you used a neural network for coming up with the abstraction from data, what abstraction would it come up with? And that's what we're interested in finding out. Would that abstraction be useful in a real sense to scale problems? And so that's where so that's the vision behind our research. And really the curiosity is, if this kind of a task-specific refinement of abstractions, by training it with examples, whether this can actually deliver us, whether this will be the solution that will actually deliver us from the long-standing and difficult verification problem. And I am running out of time here, so I will not elaborate on exactly what on the different kinds of problems that we are starting to look at. But one of them is coverage closure. And in terms of coverage closure, we have our vision again is to be able to learn how to generate tests using deep learning engine, new word for neural verification. And what we have found in preliminary results is that if you ask a neural network to just predict which parts are covered by a test, if you just give it that task, then compared to multiple, and if you use that representation learning like we have for our engine, these are some preliminary results that show that if you actually used a black box engine that doesn't understand the details of the design, like a multi-layer perceptron, or a statistical frequency, which is just guessing based on the overall frequency of whether a path is covered or not, then across the board, we find that in multiple designs, the prediction power of the first two, which are both, so the first one is representation learning, and the second one is deep learning without representations. And the first one is the overall best performer, which basically and it's able, what that means is that when you hide 50% of the design. So the 50, 80, and 90%, what do those numbers mean? When you hide 50% of the paths, it is possible for a neural network based verification engine to predict which of those paths would be covered by a given test, even if you cover half the paths. So if you say that in a new design, you have not generated tests for more than 20 or 30% of the design, it can predict whether any of your tests are going to cover the rest of the design. It can also predict, given a random test, it can tell you, it can act as an oracle and tell you with sometimes 91, 90% accuracy whether a certain test will cover a certain path or not. And this to me is mind blowing because because what we have shown here is that the neural network engine, or I wouldn't say that we have shown it because these are still preliminary results, but what we are getting an indication of here is that we have a tiger by its tail. Something very powerful is happening where the neural network is able to, with an extremely high degree of accuracy, able to estimate whether a certain stimulus can cover a certain path of the state space or not. And so being able to do this and if you think about it in terms of graphs, this is a very fundamental question of reachability. Would I be able to reach this path or not? And what we are finding is that a neural network can answer that kind of question with a pretty high accuracy. And in most of the, and it doesn't, it's much, much better than randomly flipping a coin, or which is the bottommost one, or doing slightly better or much better than that, right? So that's basically the thought and the excitement that I want to leave you with today. I think I will stop here and basically say